Hello, class 12 children. I am back now with the second chapter. We have already finished with the first chapter, that was solid state, and it took a long time, almost a month to finish that chapter because we had very less number of classes. Now we are starting with the second chapter, and the name of the second chapter is solution. Now this chapter is very important for you with respect to your board exam. There are at least 3 numericals which are coming from this chapter alone. I am saying at least. Now sometimes it can be more than 3, but yes, what we have seen generally, they give 3 numericals. You see, I am not talking about theory, only with respect to numerical, only 3. Generally I am saying yes, there might be 1 year or maybe somewhere in the middle where only 2 question numericals had come from this, but then mostly generally what happens is 3 question in IS is what is asked from this chapter. That is why treat it as very important. Now since the term is not new to you, solution is, you are not hearing it for the first time. Even in class as low as class 6 or 7 you have heard about solutions. Now you have learned properly in detail about different types of solution in class 9, so you know or you have an idea about what is a solution. Now our solution is consisting of, generally misconception that we have about solution is that okay, solution is a liquid, but it is not necessary that all solutions are liquid, because solution can be in the form of solid, solution can also be in the form of gases, a solution can also be in the form of liquid. Now let's see the misconception that you have, then after that I am coming to the definition of solution. Usually you know that a solute, okay, like for example you will think, whenever you think of solute, we will think about salt. Okay, a salt is dissolved in a solvent, and generally we think that solvent is water, then we will get a solution. A solution, and the solution here is your salt solution. So that means a solute is dissolved in a solvent to give you solution. Yeah, that is true. But then generally what we think that this is only a liquid, or solution means only liquid possible. But as I said, it can be solid also, it can be gases also, it can be liquid also. So we are going to see that in detail, but before that let us define what is solution. A solution is defined as the homogeneous mixture. Homogeneous means same throughout the bulk of the liquid. Homogeneous mixtures of 2 or more than 2 substances whose composition can be varied up to a certain extent. Whose composition can be changed. Varied means changed to a certain extent, not beyond that. So that means if the composition of that particular solution, if it can be varied, changed up to a certain extent, and if the whole solution component is homogeneous, same throughout, then we say it is a solution. Then if that is so, a solute and a solvent will give you solution. So as I was telling you about the misconception that we have, that every time we think that a solution is a liquid, but now think about different component, like for example alloys that you have learned about in class 10. Even an alloy is a solution. Alloy is a mixture of 2 metals. For example, brass is a mixture of zinc and copper. So if one of them is taken as solute, the other one is taken as solvent. Because a solution can be in the form of a liquid like this. So our solution is a liquid. It can also be a liquid solution, it can also be a gaseous solution, and it can also be a solid solution. That means your solution can be in all 3 states or all 3 phases. It can be in solid phase also, it can be liquid phase also, it can be gaseous phase also. That is why when we are differentiating, when we are classifying solution in terms of its physical state, means either solid or liquid or gas, then we say solutions are of 3 different kinds. They are in terms of whether a solute is a solid, or the solvent is a solid, or liquid, gases. So this 3 combination, that's why to understand the classification of solution, so I think I'll roughly classify it something like this. Nature of the solvent, first I'll discuss with solvent, then nature of the solute, then we will also discuss about some examples related to this one. Let's see examples. Alright, so then if the solvent is solid, also one more thing, so one confusion that most of the time we have here is, sir, how do we know
when it is a liquid and a liquid, when a solid is also liquid and a solvent is also a liquid. For example, when alcohol is mixed in water, then it becomes an alcohol solution. Then how do you know out of the two which one is solute and which one is solvent? Both of them are liquids. Okay, when it is solid and a liquid, then we understand, okay, solid is solute, whereas liquid is the solvent. But when we have a liquid and liquid, or a solid and a solid, or a gas and gas, now how do you know which one is a solute and which one is a solvent? A small understanding that you have to know is that out of the two, whichever is in greater amount, if both of them are in the same state, whichever are out of the two, whichever is in a greater amount, greater quantity, that is what is solvent. That means if water is in greater quantity, then it becomes solvent, this becomes solute. But if alcohol is in more quantity, more alcohol and less water, then alcohol becomes solvent, so then that becomes solute. That's why usually when both the components are in the same phases, solid, solid, or liquid, liquid, or gas and gas, then we look at the quantity. The quantity will actually decide which one is a solid, solute, and which one is a solvent. So here, if the solvent is a solid, so then here a solid may be of three things. It may be a solid, it may be a liquid, or it may be a gas. So that means a solid in a solid, a liquid in a liquid, a liquid in a solid, then a gas in a solid. That means greater quantity is solid and lesser quantities are this. So this is also a solid. Then, now so since we are discussing about 9 different kind of solutions, here 3 solutions came here only. A solid in a solid, a liquid in a solid, and a gas in a solid. 3 came here only. Now let's see. The solvent happens to be a liquid. Solvent, greater quantity is liquid. Then here again, this can be a solid, so we'll say solid in a liquid, or a liquid in a liquid, or you may have gas in a liquid. So again 3 here. So 3 there, 3 there. Now you know what the next 3 is going to come. So if the solvent is a gas, then if the solid is a solid, a liquid, or a gas, then how to say a solid in a gas, or a liquid in a gas, or a gas in a gas. So 3 different kind of solutions. Now I think it will be much more clearer now if I give you an example. Now how do you, so again don't forget solid in a solid. Now how can a solid and a solid be a solution? Yes, they are. For example, you have heard about gold, and then this girl will be really the air. And you know, if it is made up of 24 karat gold, which is considered as very pure gold is very weak. It's very fragile in quality. So that means you know that it can bend very, very easily. These girls were well enough. So whenever that they are wearing the earring, so you know, or ring. You know, this ring will get bent very, very easily because of this fluidity. Now, in order to give the strength to this gold, we add some components, mixer. We add some extra component. Now, for example, in that gold, if you are adding copper, or if you are adding platinum, then the gold which comes out, now you are mixing it either with, as I said, for example, any other example than copper. If you are mixing with copper, then the gold which will come out is what is impure, where it has its component in the form of copper as well as gold. So that means copper is also solid, whereas gold is also solid. A solid in a solid. So that means you can call this one as a mixture of gold and copper, or you can also say a mixture of platinum and gold. Such many other, and in class 10 we have learned already about something which is called alloys. So that means just now I gave you an example of alloys. What are alloys? Alloys are mixtures of 2 or more than 2 metals, and sometimes alloys can also be consisting of non-metals. For example, you know about steel, carbon is what is a steel component. So that means, so if I give you an example of a solid in a solid, then you can say alloys. Now it is strange, but even alloys are nothing but solutions. So many alloys, you know, brass, you know, bronze, you know, what they are. All solid and solid. So that means when a solute is there and a solvent, your solid is there, then solid in a solid, that is the example. Any alloy, by the way, I am not particularly mentioning one particular alloy, but then yes, don't give here an example of an alloy where there is mercury, because mercury is not solid. So that will come in the category of liquid and solid. Mercury is a liquid. That's why if I go to the next example, what kind of a solution is a liquid in a solid? A liquid in a solid, same alloys, but then you can say amalgam. A sodium amalgam is an example of sodium and mercury. And mercury is in lesser quantity, sodium is in more quantity. That's why sodium is going as a solid, as a solvent, and liquid is mercury. So sodium amalgam is a mixture where one of the component is mercury. Now similarly, a gas in a solid. You have heard about the characteristic of palladium last night, hydrogen chapter. Palladium has that tendency to absorb a lot of gases in its surface, especially hydrogen. So then when hydrogen gas is absorbed on the surface of palladium, palladium is a solid, hydrogen is a gas. Little quantity, this is in more quantity. But a gas, hydrogen is in solid, which is palladium. So this is an example where the gas is what is the solid and the solvent is the solid, that is a palladium. Palladium is a metal, so the hydrogen is absorbed on the surface. So this is an example of this third solution of solid as a solid. Now going on to the next one, if liquid is taken as a solid, more quantity is what is taken as a liquid, then here if I am going for the first solid in a liquid, I think this is what is the most common example. For example, sodium chloride, or you can simply say salt solution. In salt solution, solid is our salt and liquid is water. Salt and water. So salt is in less quantity and water is in more quantity. That's why it has become a solvent. The salt has become a solid. Then next one, liquid and liquid. Many examples. So if I give example of alcohol and water, which I gave is also that example of alcohol and water. So many, the juices, many different fruit juices and juice and water, those fruit juices and water, sugar cane, juice, if you are talking about. So all those are an example of liquid and liquid. But then alcohol and water. So alcohol and water is a liquid and a liquid. Now by the way, out of the two, which one is solvent, which one is solute, it really doesn't matter. Because if this is in more quantity, this becomes solvent. If this is in more quantity, then this becomes solvent. But here since we are discussing liquid and a liquid, so both of them are liquid. So any one can be in larger quantity. What about gas in liquid? Now you have heard about different solubilities of gases. In last time only two gases which are very highly soluble, what I have seen. One is ammonia and the other one is HCl gas. They are very highly soluble water. But not only these two gases, even carbon dioxide is soluble in water. So that means when gases becomes solid in water, when they dissolve in water, then the one which comes out, even your aerated drinks, when we talk about carbonated drinks, they are cold drinks. They are nothing but carbon dioxide pressurized and dissolved in water. So, or you can talk about soda is that only carbonated drink. So if I am talking about this one, this you can write carbon dioxide plus water, or HCl plus water, or ammonia plus water, you can write anything. There it is, gas and liquid, gas and liquid. So we have finished with 6 different kinds of solution. Going further now, the last thing, where the solvent happens to be a gas. Now when the solvent happens to be a gas, and if the solid happens to be a solid, now what example can we give? Now we can give an example of naphthalene balls. Naphthalene balls, you know what they are? They are used as a moth repellent inside the cupboard where you are putting your clothes. So it will repel the moths, cockroaches. Then those naphthalene balls, now when naphthalene balls are kept, remove the plastic cover and then when you put inside the cover, naphthalene balls it comes in contact with air. So that solid naphthalene ball, when it comes in contact with air, more quantity, naphthalene is less quantity, solid, so solid in a gas, So is an example of naphthalene ball you mix in air is what is an example of solid in a gas. Next one is a liquid in a gas. Now how can you say an example of liquid in a gas? Yeah, this is not a very common example you won't see, but then we have heard about chloroform. Chloroform is a liquid. You see in the lab, chloroform is kept in the bottles. It's a liquid. But immediately when you open the lid of chloroform bottle, chloroform comes and mixes with air. And that can be dangerous if you inhale that. So you become unconscious, makes the person unconscious. So then when chloroform, which is a liquid, when it comes in contact with atmospheric air, it is a case where a liquid, chloroform liquid comes in contact with gas. So greater quantity is air and less quantity is chloroform. So chloroform and air mixture is a solution where the solvent is gas, since it is air, and the liquid is what is chloroform. And finally, a gas and gas. So you know, two gases when you are mixing together, it gives you a gas and gas mixture. Our atmosphere itself is a mixture of many gases, nitrogen, oxygen, carbon dioxide, and so many other gases. So that means you can say atmosphere is an example. Then I can write atmosphere. Or any two gas you can mix. For example, carbon dioxide and oxygen, or nitrogen and oxygen. In fact, the air that they exhale or the air that we inhale, you know, they are also consisting of mixtures of gases, especially air which we exhale. It is not only carbon dioxide, you have carbon dioxide, unused oxygen, water vapor, so many gases. So those mixtures together is a gas and a gas, a gas and a gas. So if you see now, here you will find total 9 different kinds of solutions. These are the kind of solution. And don't forget, solution may be categorized into so many other forms. But I classify this solution in terms of this phase. Now when I say phase, I mean to say states. Solid or liquid or gas. So in terms of the state or the phases, you know, the solutions can be categorized under this 3 different. So this is what is classification of solution in terms of this phase, in terms of the composition, what they are. They are solid, liquid, and then they are all together in 9.
Now our next topic is concentration. Now what does a concentration of a solution mean? Let us take this example. You are going to somebody's house and they will offer you tea. But before they offer you, they will ask you how much of sugar would you like to have in your tea. Then you will answer 1 teaspoonful. Then your friend, the other friend may answer 2 spoonful. Now that means in a cup of tea, you want 1, whereas your friend want 2. That means in the same quantity of tea, same quantity because the cup size will be the same, since it will be the same size of cup. So you as well as your friend will be using the same size of cup. So in the same quantity of liquid, here 1 teaspoonful is going, the other one your friend is using, in fact he is getting 2 spoonful. So in that case, now what happens, we will say the concentration of sugar, quantity of sugar is more in the second case as compared to the first case. Therefore we say concentration of sugar in the second solution is more as compared to the first. Now this concentration may be expressed in different form. So that is why our next topic actually is the method of expressing concentration of solution. What are the different ways in which you can express the concentration? So again, since the topic is not new to you, you have done this in class 11 also. So I'll be discussing here around 6 different topics, even though there are maybe about 10 different ways in which concentration can be expressed, like for example ppm, part per million. I'm not going to discuss, I'm not going to stress too much on formality that is used especially with respect to your class 12 numericals. So but then something which are required, those only is what I'm going to discuss with you now. Now the first way in which you can express the concentration, this sugar here I said 2 spoonful in 1 cup. So it is 2 teaspoonful in 1 cup per cup. But in this way, teaspoonful is not a proper, because some spoon may be bigger, some may be smaller. That is why we may express this in terms of gram, we may express this in terms of mole, we may express that side in terms of liter, we may express in terms of ml, volume, weight. So many different ways are there in which you can express. So that is why now we'll see top, I would call it as the most important 6 different ways in which concentration of a solution can be expressed. Now the first and very common way in which a concentration can be expressed is in terms of percentage. But percentage itself is of 2 kinds. One is percentage weight or percentage mass, and the other one is percentage volume. So that's why I'll categorize this under 2 headings. So the first one is percentage by mass. Now this percentage by mass, what does it mean? We call this as W by W. So weight of the solute and the weight of the solution. Then how do we express this? For example, in a particular container, in this container, how much of liquid have you taken? Liquid, solvent that is. And how much of solute are you adding? When both of them are expressed in terms of gram, expressed in terms of weight. By the way, again I am repeating that we are not very particular about weight and mass. In physics, you know, we are very particular what is what weight, what is mass. You know, your physics teacher will be very angry if you use weight instead of mass. But as such here in chemistry, for our convenience, even mass, even though here I am talking about mass, but I am writing W and W because most of the formulas I will give you in terms of W. That's why here we don't care actually what is mass, what is weight. Both of them will say express in gram. If I say 20 gram, your physics teacher will tell you, hey, that is not weight, that is mass. But here, even though I am saying I am writing weight, but still actually you have to understand that I mean to say mass throughout the chapter. Wherever I say weight, for convenience W, because M stands for molecular mass also, so double M will come, one M for mass, another M for molecular mass. So that's why to differentiate the two, all masses of the substance I will be distinguishing with respect to small w and capital W. Small w standing for weight of the solute, capital W standing for weight of the solvent. Alright, so the way in which we can express the percentage by mass is weight of the solute. Here it is, the formula is, so by the way, even though I said weight, yeah, but the correct one is mass. Mass of the solute over total mass of solution. What is the total mass of the solution after adding the solute into the solvent? Now a solution is coming out. What is the total mass of that solution? And since we are expressing in terms of percentage, so you have to multiply this with 100. This is the first way in which we can express the concentration of a solution. Now the second way in which you can express the concentration is percentage by volume. But percentage by volume itself is of two kinds. One is volume to volume ratio and the other one is weight to volume ratio. Now let us see one by one. The first kind is, we call it as weight by volume ratio. We call it W by V. So solute will be taken in terms of weight, that is mass, and the solution will be taken in terms of volume. That is why if you want to express this concentration, then it is weight of the solute that you are dissolving divided by total volume of solution. Now you can see we are expressing in terms of volume. That was in terms of mass, here it is in terms of volume, and since we are expressing in terms of percentage into 100, so that was weight to volume, that is what W by V. Now the other percentage by volume is called V by V, meaning volume by volume. So here now you will see the difference. Volume of solute, usually this happens for all three, whether it is solid or liquid or gas, but more so for liquid and gases, by total volume of solution into 100. So this is another way in which you can express the concentration of a solution. So again I am repeating, there is a difference between the two. Here it is volume, here also it is volume, but then numerator if you see, that is weight by volume, this is volume by volume. Volume of the solute, volume of the solution. That is weight of the solute, but volume of a solution. Now in addition to this, now something which you have already done in class 11 are the concentration like molarity, molality, formality, then you have mole fractions. Now these are the one that we are going to discuss now. So even though we have done in class 11, but again since it is there in class 12 also, and most of your numerical will be having this one, normality, molarity, molality. So let's see now what they were. So a molarity is also the expression for concentration. So when somebody tells you molarity, then it is nothing but concentration of a solution. Now before I go to molarity, first let's discuss about moles. Okay, again a revision of your class 10 and class 11. Here in class 12, whenever I am writing a small n, please understand that it is standing for number of moles. It may be number of moles of the solute, or it may be number of moles of the solvent. Capital N is standing for number of moles of the solvent. Then how do we calculate number of moles? When weight of the substance is divided by its molecular mass, for example, if I want to find out what is the number of moles of sodium chloride. Now supposing if you are given 40 gram of sodium chloride, now you know you are given the weight of sodium chloride or mass of sodium chloride, but I want to find out what is the mole, number of moles of sodium chloride. Then what I will do, yeah, weight is 40 gram and I will divide by its molecular mass. Molecular mass means sodium chloride. Sodium is 23, chlorine is 35.5. So as you add 23 plus 35.5, and if you divide 40 by the addition between the two, that is what is going to give you number of moles. So that means easy formula, shortcut formula, direct formula. Whenever you are finding number of moles, always divide the weight of the substance, divide by its molecular mass. Weight of the substance, when you divide by its molecular mass, you are going to get the number of moles of the solute. Same way if you want to find the number of moles of the solvent, Then it is capital W, weight. As I told you, capital I am going to use, symbols I am going to use for solvent, and small is what I am going to use for solute. So weight of the solvent when divided by its molecular mass. See, capital M here is standing for molecular mass of the solvent. Capital W here is standing for the weight of the solvent. So that is how you will calculate the number of moles. Alright, coming back to molarity. Now what was the definition of molarity? We define molarity something like this. It is defined as, I repeat again, molarity is defined as number of moles of solute dissolved in 1 liter of solution. So in 1 liter of the solution, how many moles of a solute is dissolved? So then the formula of molarity becomes something like this: number of moles, here small n, and divide by volume. So V here is standing for volume of the solution. And don't forget, it should be in liter. In case if you are given volume in cc or ml, don't forget to convert it into liter by dividing it by 1000. But then it is not necessary that every time you will be given mole. You may be given, instead of mole, you may be given weight. So that is why this n also I am going to replace. So most of the time, rather than using this formula, n, there it is, n is W by m. So this n, if I replace with W by m, and the lower side you have V. So that means molarity formula is here. Molarity is weight of the substance divided by its molecular mass. Again, please understand that m is not mass. That is why there will be a confusion. I told you already before. There will be a confusion between mass and molecular mass. All m that I am going to use is molecular mass. Yeah, again, different book will use different symbols. Okay, it doesn't mean that again I am using this means you have, it is hard and fast rule that you have to use this. But I would prefer to use small w, capital W for weight, that is mass. And I would prefer to use this small m and capital M for molecular mass. So for me, whenever I am writing this small m and capital M, then you have to understand that this is standing for molecular mass, not mass. Molecular mass means RMM, relative molecular mass. And this is what is volume. So this is what is your molarity. Molarity, number of moles of the solute dissolved in 1 liter of the solution. Similarly, molality. So only difference between molarity and molality is that here it is in 1 liter of solution, there it will be in 1 kg of the solvent. So here it is defined as number of moles of the solute which is dissolved in 1 kg of solvent. So 1 kg, that means the formula of molarity will be now mole, then n by W is what I am going to use. But then since I am going to replace n with W by small w by m, so let me write down here small w by m is what is going to give you the number of moles of the solute. And I have to express in terms of the weight of the solvent, and then you know weight of the solvent is what is capital W. That is why I'll multiply this with capital W. So see the symbol that I'm going to use: small w, weight of the solute; small m, molecular mass of the solute; capital W, mass of the solvent. But this mass of the solvent must be in kg. Again, I'm repeating to confuse you. They may give you in gram. Don't forget to convert that gram into kg by dividing this by 1000. If it is already given in kg, you will keep it as it is. But in case if it is given in gram, you will convert that gram into kg. So this is 4 different ways in which you can express concentration. Now we have some more. Next one is here normality. Now normality uses is equivalent mass. And what is equivalent mass or gram equivalent mass? Okay, I don't want to go into detail about what is equivalent mass since you have learned that already in class 11. Equivalent mass, gram equivalent mass. Gram equivalent mass is equivalent mass. Whatever is the weight of the substance, that weight of the substance when divided by the equivalent mass, that is what is going to give you gram equivalent, or we call it gram equivalent mass. Okay, then, so what is normality? Normality is defined as the number of gram equivalent of solute which is dissolved in 1 liter of solution. So it's very similar to molarity, but in molarity you said number of moles. but for normality you have to say number of gram equivalent. Then if you want to find normality, then I'll have to find gram equivalent weight. Gram equivalent weight is small w by E. Here E standing for the equivalent mass of the solute, even though I'm using capital here, but it is standing for solute. And then V. V is standing for the volume of solvent, and this must be expressed in liter. As you can see, liter. In case if it's given in ml or cc, convert it into liter. This is what is normality. Then comes formality. I am not going to do anything now. Same in formality, it is number of formula weight. So, but since you will hardly come across any question or any numerical where formality is asked, so that's why let us not discuss. Now, going on to the last and the most important one with respect to this chapter, with respect to your colligative property, with respect to especially the first colligative property, that is your vapor pressure. So, let's see what that is, and this also something which you have already done, and this is what is called mole fraction. Okay, so to define a mole fraction, first I'll give a simple example. Let's suppose our solution is consisting of two components, A and B. Sometimes it may be more than two, it may be consisting of three components, A, B and C. But let's suppose here we have two components. Now what these two components are, A and B. Let's suppose the number of moles, I am not talking about weight, I am talking number of moles. Number of moles means weight divided by its molecular mass. Here 5 is what is the number of moles. Okay, number of moles of A is 5. 5 moles of A is dissolved in 20 moles of B. Let's suppose this is 20. So 20 moles of B and 5 moles of A, they are mixed together to form a solution, AB. Now if I want to find out what is the mole fraction of A, so if I want to find mole fraction, by the way, mole fraction is expressed by the symbol X. If I want to find the mole fraction of A, then it is defined as, so it's now say this is the definition, it is defined as the ratio of the number of moles of the component. Since I am finding the mole fraction of A, so first component, so number of moles of A to the total number of moles present in the solution, and the total number of moles present in the solution is number of moles of A plus number of moles of B. So this number of mole, again, what is mole fraction then? It is a ratio between the number of moles of that particular component to the total number of moles present in the solution. Similarly, if I want to find the number of moles for B, then since I am calculating for B, so there it should be NB. So number of moles of B to the total number of moles which are present there in the solution. Now for example, if I want to find in this example what is XA, mole fraction of A, then NA is 5 over, this is 5 plus 20. So that is 5 by 25, which if I cancel it is 1 by 5, or you can say it is 0.2. So number of moles of A in this solution is 0.2. Similarly, if I want to find number of moles of B, then number of moles of B is 20 over 5 plus 20. So that is what is 20 over 25. That if you cancel it, it will give you 0.8. Okay, I am coming to that a little later, but then just now what I defined or what I have said about mole fraction is defined as the number of moles of that particular component to the total number of moles present in the solution. Here in my example, I gave you only two components, but sometimes it may be three components, A, B plus C. Then in that case, if you want to find mole fraction of A, then mole fraction of number of moles of A over number of moles of A plus number of moles of B plus number of moles of C. Here also A plus B plus C. This is how we find mole fraction. Now notice one thing now there. Number of moles of X, A and XB, number of moles of A and number of moles of B. If these are the only two components present, if only two components are present, then the total number of mole fraction of a solution is always equal to 1. You can check it now. See, there I calculated this as 0.2 and XB came as 0.8. That means 0.2 plus 0.8 is coming 1.0. 1.0 is what is 1. So that means if I know the mole fraction out of the two, if I know mole fraction, any one mole fraction, if I know XA, I can find XB. If I want XB, if I have XB, then I can find XA. For example, let's suppose in a particular question, if all this number of moles and all are not given, but you are given directly mole fraction of B, and you are asked find what is the mole fraction of A, and here you are. If you want to find mole fraction of A, take this XB that side, 1 minus XB. See, was it really necessary to find XB? It was not necessary. After I have got XA, after I found the mole fraction of A, I could have directly told you 0.2 means mole fraction of B would have been 0.8, because 1 minus 0.2 is what is 0.8. Directly the other one would come. So that is why only when two components are present, then if you know the mole fraction of one, the other one can be easily calculated by subtracting the other one from 1. If 3 are present, supposing if XA plus XB plus XC, if 3 of them are there, that is also equal to 1. So that means if you know 2 of them, then the third one can be calculated. So add these two, take it that side, subtract, you will get the third one. This is what is your mole fraction. So today I'll wind up here, and this is only a theory part. So today I discuss only theory. So in our next class I'll be discussing Raoult's law, which contains some numericals, Henry's laws. Then after that your main chapter starts, and that is your colligative properties. So in colligative properties there are many numericals. You have to practice as many as possible. As I said, there is no other chapter which is as important as this chapter with respect to your numericals. So at least 3 numericals. See, I will not say now if you don't start searching IISc and 3. Yes, most of the IISc question has 3 questions, but then there might be some IISc where they had given only 2 numericals, but definite 2. But in most of the cases you will see IISc question has 3 questions numerical. I am only talking numerical. Theory already you know some more questions are there from theory from this chapter, but I am only talking about numerical. So that's why treat it as very, very important. So that's why don't neglect, seriously practice numericals. Since today I have not discussed anything, so maybe yes, in our next video, so when I discuss maybe in that Henry's law and your Raoult's law also, a little bit of this one. Since Raoult's law already is a part of colligative property, so that's why I think as we start Raoult's law, I think we will be coming across some numericals. Okay, so I'll wind up here today. So I'll see you now in the next video or in the next class. Thank you.